Okay. Basically, we are in week 6, as I mentioned earlier. So this week, our target is to discuss on the measurement of uncertainty in terms of reduction and quantification of systematic error. Actually, we have two parts here. The first part is to know how to reduce the systematic error, and the next part is how can we quantify the error, and how do we combine all the systematic error and come up with uh, a value of systematic error, or how do we quantify that systematic error if we have a few factors involved to contribute into the systematic error. Okay, here are the details of the content. So the first part, as I mentioned earlier, it's more on methods of how can we reduce the systematic error, and the one that I presented in this slide is basically a basic. I mean, the description is very basic, and if you like to know it in details, you can have a look at the textbook that I provided, or the materials that are provided in week 4, if I'm not mistaken, chapter 3, Reza Langgari book. So you can have a look at that one as well. And later on in part 2, basically part 1 and part 2, maybe it took about half an hour or 45 minutes to finish this one. And in part 2, basically the main target here is how do we calculate the overall systematic error, given that we have a few components of systematic errors that contributed into our measurement. So how do we combine all those and come up with overall systematic error? Okay, in general, not in general, but for introduction, there are several ways for us to reduce the systematic error. Here are the techniques that we try to do. Maybe in the early stage of our instrument design, we can properly design so that the systematic error can be mitigated or can be reduced. And also, if we have already, if you're not involved with the design, maybe we just purchase the instrument, maybe we can recalibrate. Maybe we can recalibrate our instrument in order to reduce the systematic error. And there are others like method of opposite input, which I will explain later on. Maybe also we have high gain feedback, where we try to include a feedback system in our measuring system. Also, if we have a look at our measurement, if the measurement is distorted with noises, or with noises at a certain frequency or at a certain frequency range, maybe we can introduce a filter, this known as signal filtering as well. And we also have correction of output reading. Maybe we can do it manually by correcting our when compared with our calculation, and also with the reading that we have. And also intelligent instrument. Of course, intelligent instrument, with a single press of a button, you can recalibrate, you can maybe correct our instrument measurement in an instant. Okay, here are the factors for reducing our systematic error. First, maybe we will consider redesign our instrument, but bear in mind that if you try to redesign our instrument, it will involve cost. So, of course, in certain case, maybe we need to do the redesign, but in typical case, we don't need to do that because we just extract any errors or systematic. We just predict the systematic errors of our purchase instrument. Sorry for that. And for no design, as I mentioned just now, we have a few techniques. Maybe we try to accept the reduction of measurement accuracy, but however, maybe we can also do some strategies. I mean, set up a strategies to mitigate or to reduce the effect of the errors, systematic errors in particular. Okay, first we talk about calibration. I think everyone knows that the calibration maybe can be due to environment and also maybe to the wear and tear issue. Maybe you purchase the items for a long time, maybe 10 years back, means that you need to recalibrate. And by recalibrating, you can reduce the amount of drift over here mentioned. By increasing the frequency of recalibration, we can reduce or we can like control the drift of our measurement in our measurement. Methods of opposing inputs. Maybe this is also one of the techniques to reduce the systematic error. And this is example. In this example, we try to add compensating resistance. Okay, if you look at the description over here, compensates for the effect of environment input in measurement system by introducing an equal and opposite environmental inputs that cancel it out. So actually the original problem is that our measurement has systematic error due to the environment, and we try to add a resistor which is it has a temperature coefficient which is equal to or equal to the bias that we have due to the environment, but in opposite sign. So in that case, we can compensate what the effect of the temperature of our meter or our measuring instrument. So this is you can find another example in different application. Okay, the next one is high gain feedback. Actually, for high gain feedback, normally what happened over here, for example, in our system for open loop system, open loop means that we have amplifier, coil, and spring. If what do we expect that if we have input of over here, no, I need to have my right tab. It's okay. If we have input like over here, okay, over here, maybe here is our input, and we would expect our output to be over here. Okay, maybe I try to write something over here. Input. Let's say this is our input, and we would like to have our output over here. Okay, but in practical situation, normally the amplifier will be exposed to disturbance, the coil also will be exposed to disturbance, and the spring also will be exposed to disturbance. So D over here is considered the disturbance for these particular modules. So anyway, if we do have this disturbance, meaning that if I put input, let's say I would like, let's say this input is 1, the original one. And my output, let's say with the amplifier, so on, let's say I tend to have output of 10, for example, yeah. So due to this all disturbance, I cannot have this actual value of input and output relationship. So what I would have is that maybe my output with plus, maybe plus of my or minus, yeah, plus or minus um, the disturbance, d a plus d b dc plus ds. So my output should be looks like this. Might be looks like this. What happened to here? But maybe I should decrease. Okay, this is the expected output that I would get due to the disturbance, due to maybe this maybe 10 plus the influence of dA, dC, and ds. So in order to eliminate this disturbance, what I can do is that I can make a feedback and then put a gain on my feedback over here in order to compensate this disturbance. So this is what we call as high gain feedback system. Basically, we tried, if you read over here, high gain feedback techniques are often very effective way to reduce a measurement system sensitivity to environment. So disturbance is considered sensitivity to the environment as well. However, that is the implementation of this high gain feedback is not as easy as we look over here. Just put in a feedback device, put a gain over here. Not as easy as that, because we also will be encountered with another problem known as instability in our system. I think to get in details of these terms or of this knowledge, I think you need to get into a control system courses as well. So now maybe let's accept that for high gain feedback, a potential problem is that it will make our system have instability potential. So carefully choose the value of the feedback gain that we have over here. By the way, I also teach control system design in your maybe fourth year lah. All right, and another one is the way we reduce the systematic error due to, for example, in this case, the error is due to the noises of certain value of frequency. So what we can do over here, if you look at the outputs of our circuit, it's like oscillating, and the oscillating pattern is from the oscillating pattern, we know that this is due to a 50 hertz or maybe 70 hertz distortion or output corruption. So what we can do, we try to filter all the disturbance due to that particular frequency by introducing a filter. And in this case, the best solution for siphoning or try to filter the particular frequency is by using band stop filter. Okay, if in general, yeah, in general, if we talk about filter, we have a various type of filter, several type of filter that we have that we have lah, and we have low pass filter, we have high pass filter. For example, the basic one is low pass and high pass. Low pass means that it only allow a signal with a low frequency to pass that filter. And on the other hand, for high pass filter, it only allow the high pass frequency to pass that module or to pass that filter. And in other words, other than that, they will block that frequency. So in this case, we suggest that we use a band stop filter. Means that we combine the idea of low pass and high pass to come up with a filter known as a band stop, where we only stop that particular frequency of our to get our output clean. So here, if you look at the figure A, we have, for example, it says here 50 hertz corruption or 50 hertz oscillation. So we need to have a band stop, band pass, not band pass, band stop filter in order to stop this 50 hertz oscillation. So now we are going to have a clean outputs in our measurement. Right. And this is a manual correction. As I mentioned earlier, we need to do some calculation. But of course, if we try to use a manual calculation, it's not that easy. We need to take an account all of the disturbance in our measurement. We need to quantify all the potential factors to distort our measurement. And the last one is intelligent instrument. As I mentioned earlier, maybe intelligent instrument is like a cheat code lah. Just a single button and it will try to eliminate all the systematic error, all the errors in our measurement, and we try to give us the best output data, that output measurement that we should get. However, of course, for intelligent instrument, it's quite pricey, and maybe in current case, for if you try to if you are in very demanding industry, maybe this intelligent instrument is of course the first choice of measuring instrument. However, if you just inventor maybe or try to learn about measuring instrument, maybe it's quite a burden for you guys to purchase this intelligent instrument. Okay, in general, as I mentioned in previous slide, we have several methods. So you need to, if you want to know the details, you can have a look at Reza Langari book. I think in chapter 3, it's describing about all the reduction method. Maybe Reza book also not enough. Maybe you can also have a look at videos, I think from Indian professor. I think if you have a look at YouTube, you can find that one as well. At the moment, I think Reza Rangari book is quite enough for our course. All right. Any questions so far before we proceed to our second part?
Doctor.
Yes.
Can you re-explain the high gain mechanism? If I'm not, tak tahu lah, because from what I understand, before the macam ni, output itu dia akan loop back to the input. Is it some of it, or?
Okay. Let's say over here.
Yes.
Yes, over here, this is the output. let's say, okay, let's say we don't have this element, yeah? We don't have this element, we don't have this element as well. Okay. This tree module is known as an open loop system. Open loop system, where originally, if we have input 1, let's say 1, and without these three disturbances, maybe our output will be the actual value or the value of 10, for example. And since the amplifier itself will introduce some noises as well as coil, maybe electromagnetic problem, and also spring, maybe elasticity problem. So we try to predict that all these three modules will introduce disturbance. So the output that we will get is not 10, the actual 10. Maybe we'll have 10 plus all these disturbance factors. So what we can do is that we try to eliminate, partially eliminate, not 100% eliminate, but this is part of the strategy that we can use. What we try to do is we try to feedback the output over here and try to make it like this. The difference between the our reference or our input, now our input is over here, and we try to take the difference of our input and also the feedback output, and the output that we take as our as the feedback must be multiplied with the gain, and this is known as the feedback gain. So this part is the feedback gain, and remember that the feedback gain also will introduce disturbance. That's why I say just now it's not 100% eliminated, but it's part of the strategy to reduce the what do you call it, influence of disturbance in our system. So the selection of this feedback gain also very crucial. If you choose the value of gains that is too high, maybe yes, you can eliminate the disturbance. However, it will introduce you another problem, which is known as your system will become unstable. So there will be a trade-off between a selection of feedback and also your objective try to reduce the effect of disturbance. And in some cases, maybe the feedback gain, they try to find a feedback gain that just enough for their application. So this is not the exact, I mean, the selection of the feedback gain must be carefully selected because it will introduce a bigger problem in your system if you not choose it wisely. Is it okay?
Okay, now it's clear.
All right. Okay. Right, now we move on into our second part, and I believe we can finish our class at 3 today. Hooray!
Hooray!
Anyway, this is the part where we try to calculate the overall systematic error. The first one is I will explain about how do we quantify the error components, and later on we try to combine all the error components and try to calculate the overall systematic error. Okay, and quantification of systematic error, we have a few factors that we identify over here. One is due to environment, calibration, system disturbance, and also loading error. I think we discussed about loading error before this in last week class. All right, for environmental error, here it says that if a measurement is subjected to unpredictable environment condition, the usual course of action is to assume midpoint. Okay, the keyword here is midpoint. Midpoint environmental condition and specify the maximum measurement error as plus minus X% of the output reading to allow the maximum expected deviation in environmental condition away from this midpoint. So in other words, the keyword over here is first we try to find the maximum measurement error and take the assumption that we only count the midpoint of the environmental condition. And for calibration error, basically normally calibration we will suffer a bias from the calibration. So the idea also almost the same, I think. And okay, if you read through this text, normally calibration in the form of bias, as I mentioned, and the best way here mentioned about is to assume some midpoint value of the calibration error and compensate all measurement by this midpoint error. So again, we try to assume, that first we try to take the maximum measurement error and take the midpoint value in order for us to predict or to quantify the error due to the calibration. Okay, here are the example. If you look at this example, first it says here the question says that the recalibration frequency of a pressure transducer with a range of 0 to 10 bar is set so that it is recalibrated once the measurement error has grown to plus 1% of the full scale reading. How can its inaccuracy be expressed in a form of plus minus X percentage error in the output reading? So the idea here, our instrument, the pressure transducer, okay, the range of the pressure transducer is 0 to 10 bar and will be recalibrated if the error has grown into 1%, positive 1% of the full scale reading. What is the full scale reading? Okay, full scale reading, 1% of full scale reading is 0.1 bar. So in other words, if we try to use this instrument, if it gives us a measurement, suppose it should be 10 bar. If it gives us a measurement of 10.1 bar, means that this item or this instrument should be recalibrated. So that's what happened in the question. So now the instrument will be recalibrated if the measurement error grown to 1%. Okay, first, the solution over here, if you look here, just before the instrument is due for recalibration, the measurement error will have grown to 0.1 bar or 1% of 10 bar. Okay. This statement says that this instrument will be not being calibrated if the error measurement is not grown up until 0.1 bar. In other words, let's say if this instrument had the measurement error had grown into 0.1 bar or 1% of its full scale reading. So it needs to be recalibrated. Now an amount of half this maximum error, okay, this is considered as your maximum error. That is 0.0 bar should be subtracted from all measurement. In other words, we would like to say that the quantification, we try to quantify that we need to take half value of this full scale measurement error. Okay. Having done this, the error just after the measurement has been calibrated will be negative 0.05 bar or negative 0.5% of full scale reading. and the error just before the next recalibration will be plus 0.05 bar or plus 0.5% of full scale reading. So in other words, to answer this question, the inaccuracy due to calibration error can be expressed as plus minus 0.05% of full scale reading. I think the key things here is that we try to find what is the maximum error, and from that maximum error, maximum error can be found based on our full scale reading, and take the half of that maximum error in order for us to predict the inaccuracy. Okay. Later on, system disturbance, I think also the same. We disturbance of measured system by the act of measurement itself introduce a systematic error that can be quantified for any given set of measurement condition. And the best approach is to calculate the maximum likely error under worst case system loading. Let's say this is due to system loading system loading condition. So what we can do is that to predict or to quantify the measurement error, we take the maximum likely error first, and then take the half of the calculated maximum likely error and put it as plus and minus. Same as suggested in what we've seen in calibration error. And I think this is also the same. Okay, in order for us to calculate the overall systematic error, we will use the technique or the definition called as root sum squared method, or actually we try to take the RMS value lah, root mean square, sometimes known as that one as well. Here are the equation of the root sum squared method. We take the x1, x2, x3 consider as our measurement error. Let's say here we have x1, we square it, and plus x2, square it, x3, and up to x1. Basically, let's say this is x1 due to calibration error, x2 due to environment error, maybe, for example. X3 maybe due to loading error, and we take the square of it, make sure that the value of x over here is the half of the maximum value for that particular, for example, calibration error. So take the square of it, and also take the sum of the squares and square root it back in order for you to get the overall systematic error. I have a example over here. Let's say we have three separate, the question says here, three separate sources of systematic error are identified in a measurement system, and after reducing the magnitude of this error as much as possible, the magnitude of three errors are estimated to be, okay, for system loading, we have 1.2%, plus minus 1.2, environmental changes 0.8%, calibration error 0.1%. Calculate the maximum possible total systematic error and the likely system error by the root mean square method. Okay, before we get into the calculation, first of all, if you look at the value available in system loading, environmental change, and also calibration error, it is easy for us to say that the maximum possible system error is the sum of these three. Okay, but if you look at the question itself, three separate sources of systematic error are identified in measurement system after reducing the magnitude of these errors as much as possible, meaning that originally the system loading error is double of this value, means that it is 2.4% over here, 1.6% and 1%. And after we do some quantification, after we do some reduction technique, and also we try to estimate, we try to quantify what is the magnitude of the system loading errors due to system loading. We try to take the half value of our maximum systematic error that we calculated earlier. And that's the thing that I would like to highlight over here. Maybe it's not available in the question. Maybe you should have in mind that originally, but not being used in our calculation lah. But originally, to understand what I've been learned in a previous slide, originally basically the system loading is 2.4%. But with the reduction technique, and also after the reduction technique, we try to quantify what is the system loading error. So the value of 2.5 have been, we only take half of that value. Okay, here is that value. Here is the value that we try to take the half of our maximum original system error, system loading error. And if you look at here to answer the question, the first one, we have maximum possible total systematic error, and as I mentioned earlier, it's just by summing all these three components. And of course, by summing all these three components, you will get the solution as plus minus 2.5%. And for the likely system error by the root mean square method, what you need to do is you need to apply the formula that I showed you earlier for calculation of overall systematic error, where we try to combine all those errors. Okay, and the way that we use over here, or the way that we put in the numbers in our equation, is that for system loading we have 1.2, so 1.2 squared plus 0.8 squared plus 0.5 squared, and we take the square root of this summation, squares of summation of squares, and this is the answer. Basically, for the error, we don't know actually how much error that we have in our measurement. Okay, the one that we show over here is just an estimation. So, but it is a best practice for estimation purposes. So maybe in real situation, maybe in certain situation, maybe this approach or this technique is not applicable. Maybe you already know what is the value of your systematic error, but in normal case, it is quite hard to actually know what is the systematic error in our measurement, but it can be quantified. So the idea is by using this approach lah. All right, I think this is my second last slide. So these slides will summarize what we have learned today in part 2. The first one is we try to quantify the error component, and remember that the keyword here is first try to find the maximum error, maximum possible error, and later on take the half of that value. Okay, that is for the first part. And for the second part, for calculation of total error, maybe when we try to combine all those errors that we quantified, which quantification is basically based on assuming. When we try to combine all those 4 factors, what we can do is we try to use a root sum square method in order for us to quantify what is the overall or the combined error components value. So I think that's all for today. And do you have any question?
No, doctor.
Okay,
Dia
all right.
kot.
I know this material is a bit, you need to digest it first lah, okay?